Welcome to Embedded. I am Alicia White, here with Christopher White, and I would really like to say that this week we are roving reporters. You'll get that joke in a little while. But our guest has actually joined us in the studio. Welcome to Laughlin Barker.
Hi, Laughlin.
Hi.
Thanks for joining us over here.
Yeah, thank you for having me.
Could you tell us a little bit about yourself?
Yeah. So I'm, mechanical engineer by training in undergrad. But at the moment, I'm a systems engineer at OpenROV. We make small, low-cost, underwater, remotely operated vehicles. And I got started doing underwater stuff a number of years ago, working in the Antarctic, supporting NSF science missions, deploying ROVs and instrumentation underneath the ice in the Ross Sea, working on an icebreaker at one point, and then kind of miscellaneous contract-related underwater things in between field seasons. Thought I wanted to get my PhD at one point, and so started doing that in Baltimore for a while, and that was in underwater navigation and state estimation. Decided maybe that wasn't the right move, and then came back out to California about 18 months, about a year ago. And I've been back at OpenROV since.
Okay. I'm like navigation, state estimation, underwater, Antarctica. I have all these questions. But first, we're going to do lightning round.
Cool.
And you've heard the show, so I'm not going to explain. Christopher, do you want to go first?
Who would win in a fight, a penguin or an ROV?
Penguin.
Despite the possibility of breaking federal laws if you answer in the affirmative, have you ever pet a penguin?
No.
Do penguins care about ROVs?
No.
Who would win in a fight between a Roomba and an ROV?
ROV.
What temperature is cold?
Minus 200 C.
Hey, for me, it's 62 F.
Have you ever personally lost an ROV to the depths?
No.
Have you ever had one freeze in the ice?
No. Almost had one stuck, though.
How close is real life to the abyss?
Oh, they touch. There's a boundary there.
Does it lead to monsters?
I think it just leads to the unknown.
Okay.
Oh, but that's a boilerplate question.
Yeah, but you had a good answer, so go ahead.
All right, what's a tip everyone should know?
2 is 1 and 1 is none. That's mostly talking about spare parts.
I've heard that on mission critical things.
Yep.
Usually from military guys.
It's true in the Antarctic as well.
I imagine. Okay, OpenROV. This sounds like a company that is making underwater remote operated vehicles that are in some way open?
Yeah. So OpenROV started in 2012. Eric Stackpole and David Lang, and they launched a Kickstarter, and the idea was that they wanted to make these low-cost, accessible, remotely operated vehicles. And so they started out with a kit that first launched on Kickstarter, and it was cut out of acrylic sheet on a laser cutter. All the electrical, mechanical, and software was hosted up and still is on the OpenROV GitHub page. So in theory, if anybody had a laser cutter, they could download all the files, cut the parts out, spin your own board, all the Gerbers and schematics and everything were up there, and then flash it with the appropriate software on the SD card, and you'd be up and running with a little ROV. So that's, a pretty big barrier to entry because you need a lot of tools and stuff to do that. So instead we sold the kits. And they were these little shoebox-sized ROVs. And one of the driving themes behind this ROV was that you could fit it in a backpack. You could take it on an airplane. So we were beneath the 100 watt-hour limitation that you run into with lithium batteries on airplanes. But you could literally fit it under the seat of a commercial airliner and then take it anywhere you want. So OpenROV transitioned. We saw even with these kits when all the parts were given out to or sold to folks, there's it takes quite a bit of maker skill to be able to put it together well to withstand 100 meters of depth. And if you were very diligent, you made sure all the surfaces were good and you had good glue joints. You could make a 100-meter ROV and it would do exactly what you thought it would. But it was also tough for a lot of folks because that level of like spending an entire weekend and being very diligent and detail oriented left a lot of folks out and from that ability to go and explore the ocean. And so we thought, well, we should make something that that anybody can just buy and then literally pull out of their backpack or out of the box that it comes shipped in and be ready to go. And so that's what motivated the creation of the Trident ROV. And all of the Trident ROV development occurred before I came on about a year ago. And so things were just ramping up in actual production when I joined last year. So
there's been quadcopters and RC. That whole field has kind of exploded, and they've gotten more and more sophisticated. And the technology in those is well known. Brushless motors and the battery technology and the radio stuff's all advanced. How does an ROV differ from that? What are the hard problems about going underwater versus going in the air?
Yeah. So pressure and the corrosive and conductive nature of water, especially salt water, are the big ones. The Trident ROV it's an injection molded plastic shell, and the entire shell itself is actually a pressure vessel. And this kind of goes in contrast to traditional ROVs that have been made for a number of years, where you have cylindrical ceramic, aluminum, or other exotic material pressure housings, and then you build fairings and chassis around them. So we've got this injection molded plastic that keeps all the pressure out, and then inside we've got a Raspberry Pi, and that's what's doing most of the computing and message and marshalling for the system. Handful of I2C sensors, accelerometers. So that's very similar to the quadcopters. Also lithium-ion batteries. Again, in that under that 100 watt-hour limit. Perhaps some of the really unique things, I think, are that we take the brushless motors and they're actually immersed and in salt water. And this was one of the really brilliant things.
What?
One of the really brilliant things that I think OpenROV figured out early on was that, instead of trying to spend all of this time and energy and how do you keep the salt water out of the motor, it's like, actually, if the enamel coating on the wires is good, you can put them in the salt water and they'll run just fine. And so that was like, mind-breaking. All of a sudden, you can take these little motors and just expose them to the water, and then you just have to worry about a little electrical pass-through, across your
and that's
pressure
much
housing.
Easier.
Yes.
A couple of wires is so much easier.
Yeah.
A couple of wires that don't move.
Right. You don't need fancy shaft seals that have to deal with pressure differentials across them and all sorts of stuff. Yeah.
But unlike a drone that you fly, the Trident is cabled.
Correct.
But it's still first-person view, right? I mean, I could wear a headset and be the Trident.
Yes.
Be a fish.
Yeah. So there's a high-quality 1080p camera in the front, and it's tethered because RF is very quickly attenuated in water. It's frequency dependent, but effectively you can say that you can't pass RF through water. If you get into really low frequency, that's the game that the submarines play. But we can't do that.
That's a few bits per second anyway.
Yes, yeah, exactly.
If that.
So the tether, the batteries are all on the vehicle, and we use the HomePlug AV protocol, which is perhaps more colloquially known as Ethernet over power. And so these are little modules that you could plug into the plugs in your house, and it takes a standard Ethernet signal and modulates that over two wires.
So that's clever.
We have a single copper pair coming up from the ROV, and those tethers are either 25 or 100 meters long, and we max out the bandwidth on the Raspberry Pi B. That's the bottleneck. Actually, we could push more over the tether if we needed to. And
so the 100 meters. You mentioned it goes down to 100 meters. Is this where the 100-meter limitation comes in?
We've officially, the ROVs are good to 100 meters, and that's how long our tethers are. So that's a convenient way to keep them from going deeper. But the ROVs have gone deeper with special tethers, but we can't. They're not warranted past that. But we have taken them down to failure, and they fail. Not insignificantly deeper than, I guess Yeah, well, it's pretty significantly deeper than 100 meters. So we've got plenty of buffer there.
And it's 1 atmosphere per every 10 meters.
Yep.
So if we went to space, we would go from having 1 atmosphere to 0 atmospheres. But if we go underwater 100 meters, we're going from 1 atmosphere to 10 atmospheres.
Yep.
Is this just a gasketing problem, or is there more to it?
So the gasketing, typically in underwater stuff, we use O-rings, which are distinct from gaskets. We don't get any of the advantageous geometry that you would get from a cylindrical pressure housing. You think about what a home scale propane tank looks like, for example. It's a cylinder with curved ends, and that's because that reduces stresses that occur at all these very critical points. So ours is kind of funny shaped, and as a result, if you were to look at the inside of the Trident, the injection molded piece actually has all this very complex latticing that the engineers did a tremendous amount of FEA work on to basically make this part withstand 10 atmospheres, which ends up being approximately 150 pounds per square inch at 100 meters. And one of the interesting things is that we actually there's a big motherboard inside Trident, and we use that motherboard, that piece of fiberglass FR4, as a structural component. So these lattices are coming down and pushing on the circuit board. We cleared components away from where it lands down, but that PC board is actually in pretty significant compression to help hold everything up.
What was the reason to go that way instead of cylindrical?
We couldn't get the nice form factor that we wanted. One of the motivators behind Trident was that it wanted to be this kind of nice transecting vehicle, almost like flying, that first-person view you were talking about. And so it's actually fairly low and sleek, has a very small frontal area, which is good for drag characteristics, makes it so you can go fast. Yeah.
How fast can you go?
We can do about 2 meters a second, which is like Olympic swimmer Michael Phelps speed. Yeah, it's actually pretty hard to control when it's going that fast. So I actually like to pilot it on the lowest speed setting, because that's when you can get these, really gorgeous slewing videos and movement. Otherwise, it's pretty jerky.
You mentioned finite element analysis.
Uh-huh.
What kind of tools do you use to do that?
I believe, I don't know if they're using ANSYS or just the built-in SolidWorks modules. All that design work happened before my time, so I'm not quite sure, but one of the two.
It was always such magic, and now it's like commonplace and amazing. Yeah. Okay, so what sensors are in the bot? It's you mentioned camera, so we have camera. What else do we have?
We've got a temperature and pressure sensor, so that gives you depth and water temperature.
Doesn't the pressure sensor require you to have a hole?
The pressure sensor actually lives on the outside of the vehicle. It's kind of buried up in the plastic, and then again, it's just a small electrical pass-through across the bulkhead. And then we've got a 9 DOF, but we get 3-axis compass compass orientation out of it. So on the heads-up display, we display tilt and yaw. We don't display roll, but it's a 9-axis gyro. It's doing fusion on board, so we just take the quaternions out.
Can I ask which one?
It's a Bosch 085.
Good choice.
055.
Yeah. That's a good choice. Don't.
Oh, yeah, sorry. No, we don't like it's fine to say with the Bosch one. It's the same one we've used on the other ROVs, but yeah, we've had a really hard time with that IMU. We're not very happy with it.
Has anybody had a good time with any IMU? I'm getting the impression that they're just very difficult to work with. And it's not because the math is hard. It's just that they don't do a great job documenting stuff.
Yeah.
See, I'm using the InvenSense competitor to that one.
Yeah, the 9250 or one of the...
that
one's about end of life.
No, 20948.
Oh, that's one of the new ones. Yeah, I've been looking at that one, actually.
Yeah, it's a pain in the ass.
Okay. Yeah, you have to actually load the fusion system externally. And I was trying to think to myself, why the heck did they do that?
So they could change the code. But also, there doesn't seem to be any documentation for that code that you load. And so it's like, get the quaternion. And you're like, okay, what does this accuracy flag mean?
Yeah.
And it's nowhere.
Yeah. Do they actually give you the fusion code, or do they just give you a hex blob that gets loaded in?
They give you a hex blob.
Okay.
Must not change the hex blob.
Right.
Are we keeping this part?
Oh, yeah.
Oh, yeah. Okay. Then I should stop saying mean things. 'Cause, I do want them to help me someday.
Yeah.
Okay. So it has a IMU, pressure sensor, temperature, camera. Anything else?
Some bright forward-facing LEDs, so that you can illuminate in the dark. Yeah, that's about it.
No lasers. Sorry.
Oh, well, I mean, the MBARI, the local research, Monterey Bay Area Research Institute, has lasers on there so that they're always 10 inches apart with it where the lasers are, and they can measure things that way.
Those are measuring lasers.
Yeah, scaling lasers, we typically call them.
Scaling lasers, thank you.
Yep.
You wanted...
Yeah, the ones like the sharks
missiles
have.
Like the sharks. The lasers like the sharks have. Yeah. All right. Okay.
So you can scare the fish. So the 2.8 kit has scaling lasers on it. And that's definitely something that people can put on the Trident if they want. We've got a pattern of threaded inserts on the bottom of the vehicle, so anybody can screw on and attach payloads if they want.
And do those have power connections as well? Or okay, so
no power connections.
You can't add something that runs through the bulkhead.
Right. But there's a fair amount of capability that's plumbed in there for hackers, that could do some fun stuff. So,
have you seen anything particular?
There's some folks in the forum who are plumbing out so we use DDS as the internal messaging and marshalling system. And so some folks maybe...
I haven't heard of that. What is that?
ROS, maybe a familiar analog. DDS...
Robot operating system.
Correct, yes. DDS, I think, was... I'm not sure of its provenance or creation. I think it's used a lot in NASA as well as... military and defense applications, but it's a similar thing. It's a messaging and marshalling system. You can fine tune a lot more in terms of quality of service. You can prioritize certain messages or keep messages in a queue that then get delivered later on. But anyway, so that's the underlying.
Are you using ROS 2?
No.
Okay.
But the ROS 2 messaging system is built on top of DDS.
Yeah, that's what I noticed, and I'm waiting to find out if anybody is using ROS 2.
Yeah, I'm excited to get in there. I've kind of been waiting. I really want the introspection tools to come online before I kind of make that dive. So that's what I'm excited for. Yeah.
Wait, he was talking about things that people have done.
Sorry, I'm not going to. Don't divert into ROS. Nobody but you cares. Okay,
no, not true. So I've seen some folks playing with piping out the quaternions from the IMU, which are published on the messaging system, and we have hooks in there on our GitLab page. If you just go to GitLab/OpenROV, there's some sample code for a native app that'll run on the vehicle. This would be the equivalent of a ROS node for those familiar with ROS parlance. And there's a Wi-Fi. We don't use the Wi-Fi module inside the Raspberry Pi all the time. And so the idea was that people could bolt on payloads to the bottom of the ROV and then use that Wi-Fi. And it turns out going, back on my RF doesn't transmit through water very well. If you have
how far does 2.4 gigahertz go?
If you've got a little bit of water, like maybe a little water interface between your two housings, you can pass.
So a couple millimeters is okay.
Yeah. But if you really wanted to bolt something on and seal it, that would be even better. And yeah, because it's a Raspberry Pi, it's running Linux. The root password to the vehicle might start with an O and end with an ROV, but I'll leave it to people to guess what that could be.
Other ROV.
Yeah.
Opposite ROV.
Ostrich ROV.
Okay, so payloads. actually, I heard you speak at a Pilates event, and one of the things that kind of just I didn't understand before your presentation was buoyancy.
Yeah.
Oh,
I kept thinking, okay, so when you add a payload to a flying drone, your battery goes way down, your maneuverability goes way down. It all just, I mean, it's such a cool idea to have taco copters, but it's not efficient.
It's fine.
But with the OpenROV,
Nobody wants a soggy taco.
No.
and really, as you fly through the air, what is hitting the taco?
Air. Hopefully not bugs or birds.
But so tell me about how buoyancy is important here.
Yeah. Well, so in theory, you could get away with just putting something that's very heavy and negatively buoyant, or very light and positively buoyant on the vehicle. But then you're going to be fighting that natural tendency for the vehicle to rise or to sink in the water. So to keep your batteries happy and not drain the system, you want to have something that's neutrally buoyant. So you can, if you were to add a payload that is negatively buoyant and heavy, maybe underwater it weighs 1 pound, then you'd need to add some equivalent amount of buoyancy to the
Which
vehicle.
is just making a bigger plastic housing so you could put a bit of air in there.
Yeah, or attaching external foam. There are different, in the world of underwater vehicles, there's a whole set of folks who just think about foam and buoyancy and how do you make these foams that are going to not compress and survive, many hundreds of PSI of pressure. And then that's less dense than water. So if you attach that to your vehicle, you're effectively adding flotation to it.
But that compression is important. We've been to the Ambari open house where they have the little styrofoam cups that you decorate, and then they take them to the bottom of the trench, and then they come back and they're like little tiny
Thimbles.
teacups.
Yeah.
So how do you, that seems like a natural property of foam that it compresses.
Yeah. And so this use of the word foam may be a little liberal, but there's syntactic foams out there.
Are these ones that are very good at grammar?
Imagine foam like basically take an epoxy resin and then mix in a bunch of microscopic glass balls that are hollow. And so those glass balls that are hollow are naturally buoyant. And when you, this is basically what makes composites strong, is that as you take a material and you get smaller and smaller pieces of it, you're reducing the likelihood that you have a defect in a grain boundary or some other property that is usually where failures begin in these materials. So if you make them really small, then they, on average, tend to be close to perfect, whatever that means. And then you can encapsulate them in epoxy, and overall the structure is incredibly strong. You can machine it on a mill or a lathe, which is great, but you need good respiration. And then you can even do things like paint over them with sealing paints or additional fiberglass. So they're actually quite hard.
There's so much here. We've touched on math and ROS and foam, and how do you? It seems too big. How do you even approach this?
Yeah, it's hard.
How did you approach this? How did you get into this?
Yeah. So I got into it from a friend who I met at the Ham Radio Club in undergrad. And he called me up after I was done with my mechanical engineering degree and said, "Hey, have you had your wisdom teeth pulled out?" And I said,
what a way to start a conversation.
Excuse me? I said, "Yeah, have you had your wisdom teeth pulled out?" I said, yeah. And he goes, "Oh, great. Well, do you want to go to Antarctica in November?" And I was like, let me think about that for half a second. Yes.
That was the only major criteria?
Well, so that was the introduction. And then I actually, met with Dr. Stacy Kim, who is the principal investigator for this project. And this was based out of Moss Landing Marine Labs, not far from here, just down Highway 1. It was interesting in that initial interview that I had with Stacy. She's a benthic ecologist, so she studies the critters that live on the seafloor. And the interview questions were all about how you deal with stress and team dynamics and this, that, and the other. And I kept waiting. Well, when is she going to ask some technical questions? And then they never came. And then she's like, okay, well, you've got the job if you want it. I was kind of dumbfounded. Like, you don't even want to know if I know like what an I2C bus is or something. And, and then after my first season down on the ice, when you're, living and working with the same people for 3 months, I was like, oh, I get it. Like, it would be, having not the right skill set is by far and away better than somebody who you just can't work with, and 3 months is a long time when you have to live and work with them 6 days a week, and it's go, 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 go.
Okay, so are you living on a boat? Are you living in a tent? A tent in Antarctica?
An ice cave, fortress of solitude?
Yeah. So what's it like working in Antarctica?
So the first season we were based out of McMurdo, and it's a summer population somewhere between 800 and 1,000 people. It's the largest U.S. largest research station on the continent down there. And it's like I kind of describe it as a small mining town. You have doctors. There's a small hospital. Yeah. There are electricians and, everything it takes to run a small town. Everybody's down there, and it's dorm style housing. And then there's a big galley. So the first year we were living in town and then commuting out to our field sites on snow machines each day. And we would pull sleds that had our ROVs and instruments. So we would go out in the morning, do our work, and then come back in. The following season, after the scientists looked at some of the initial data, they seemed to indicate that there was a strong diel signal in these animals, and that means that they, not surprisingly, have a difference in how they behave, whether it's night or day. Even though the sun is up 24 hours a day, that time of year, it gets lower in the evenings, so you end up with less light making it down into the water. And so
this is like jellyfish come up when there's a full moon at night, and they feed at night high up, but then they go down during the day because they don't want to be eaten by birds.
Right.
Okay.
Yeah. And so this is with krill and silverfish, and so we were looking at critters at the bottom of the food web. And so that season we actually ended up setting up an ice camp out in the middle of the sea ice. So this is ice that freezes each year during the winter time, and it's on average like about 6 feet thick. So it's quite strong. And we had individual mountain tents set up out there, and then a food tent, storage tent, and a communal eating tent. And so we would be out there for 6 days at a time and then go into town, which is like an hour away on snow machine. It was about that far of a commute. And then, would do laundry and get a hot brunch. There's brunch served on Sundays, which is always a real good treat. So
McMurdo Station, it's where you go for brunch.
Yeah.
Where you go for anything, probably.
Okay, you're camping on an ice block.
It's summer. It's summer.
Right. So doesn't that sound like even a worse idea than camping on an ice block during winter?
It's a lot of ice.
So were there storms and stuff, or is it pretty calm during the summer?
Generally, it was pretty calm. We put in our camp the last year, and then within a few days had a big storm. And we had the real bad storms come out of the south, coming off of the Antarctic plateau, and so we had basically built our camp so that it would be more robust against a storm coming out of the south. And then this massive storm just comes out of the east and, puts all of this snow on top of us, which is kind of bizarre. There's not typically a bunch of snow out there. And I think was due in large to the wind picking it up and transporting it rather than falling out of the sky. But yeah, for the next week, part of field work was having breakfast in the morning and getting up and then digging out a portion of the camp for an hour and a half, and then going out and doing the field work, and then, coming back and repeating that until the place was dug out.
That sounds super fun. What do you mean by field work? Okay, so this wasn't the backpack-sized ROV that we have been talking about, the Trident. This was bigger.
Yep.
And more, and probably a little more effort.
Mm-hmm. Yeah. So this was an ROV called Skinny, submersible, capable of under ice imaging and navigation. And it's about 4 feet long, torpedo shaped, weighs about 35 pounds. And we can deploy it through its largest OD, outer diameter, was 8 inches.
So you'd have to drill a hole in the ice in order to get it down there, and that's how big you'd have to drill the hole.
Yeah, and so there's
How do you get it out?
Yeah, that was my question.
Tethered.
But you'd have to align it to the hole to
so
get it.
we pitch the vehicle down and then thrust down so that we basically line it straight up, and then the tether manager who's up at the surface gently guides it up. And sometimes you'll catch the bottom fairing on the ice once or twice, and you're just gentle until you guide it into the hole, and then out she comes.
Okay, so now you've dug out your snow and you've drilled a large hole in the ice. Did you have to do that every day, or did you use the same one most days?
Yeah, no, we did that every day. And the holes were made in the ice using a jiffy drill, which if you've ever used a gas-powered auger to dig fence post holes or something, it's basically a lawnmower engine mounted on handles. And then we put these
right, because you're drilling 6 feet.
Yeah.
And an 8-inch hole is not small.
Yeah, and it's actually the drill bit itself is 10 inches.
Sure.
And so we had this, gas-powered drill, and that was part of our field kit. And so we would actually have to drill a couple of holes at each field site, one where the instrument would get deployed through. And our instrument was, we were actually using Skinny as a tow vehicle to pull a larger sonar instrument that had an active, essentially an expensive scientific grade fish finder, and a fluorometer that was measuring the amount of algae in the water. And so we were running transects with this, but we would drill a hole to deploy that, one for the ultra short baseline navigation head, which is an acoustic navigation system that we would lower down through the ice, and then another one for taking water samples. So it was typically 3 holes per site. On a good day, we could knock out 4 field sites, and they were all separated, so it meant some commute on the snow machines. So we would pack everything back up, drag it to the next field site.
So these were like 20-hour days.
Not quite that long. We did have some that were long, especially when stuff broke down. Then the pressure was on. Like, I don't even want to think about what the hourly expense for having a person down at McMurdo when we're supposed to be doing science and the vehicle's something is shorted out and the engineers are like, oh, we're trying to fix it. And the scientists are like, when's it going to be ready? And we're like, we're working.
Well, and you don't want to lose it, so it's important that you fix it properly.
Yeah. No shortcuts. Or at least shortcuts with, extra belt and suspenders attached.
The underwater navigation.
Yeah.
Is that, is it just like sonar? I mean, is it just chirping and everybody takes times? Do you need a fine-grained clock to do that?
Yeah, so there's underwater navigation is a whole subject of research in and of itself.
Yeah, I hear somebody was thinking about getting a PhD in that.
Yeah. So I don't know how much we want to do like a deep dive, but essentially we have.
Is that a joke? Is it like your life full of puns?
I didn't even think about that one, but yeah, so I kind of think about the navigation space as. On the one side, you have a whole suite of sensors that you have that are available to you. I guess I should preface this with that underwater, is a GPS denied environment. So we don't have any external source of position when we're underwater naturally.
And that's so weird. Like 20 years ago, as humans, we were like, maps are fantastic. We're going to get from here to there.
Yeah.
The only way to know is to go by a map. And then we got GPS and we're like, I'm just going to shake this until it works and it's going to tell me where to go. Without ever thinking this goes to space and comes back down and has this weird calculation of multiple things in space. And now you're underwater. You don't even get this basic human right of GPS.
Well, yeah. Well, fundamentally the way an external position correction underwater works, which is the same thing that, GPS can provide velocity, but let's just talk about position for a moment, is that your GPS receiver is measuring ranges to a whole bunch of different satellites that are moving around the Earth simultaneously. And then it uses all those different ranges with a known position of where that satellite is to back out or estimate where you think you are. And in the underwater world, we do the same thing, but using acoustics. So an ultra-short baseline system, the baseline refers to how far apart the receiving elements are on your system. So it's essentially this sonar head, and it has a whole bunch of piezo transceivers packed into the head of it. And in most USBL systems, it'll work by it emits a ping of sound, and that goes out and it hits the vehicle. The vehicle has a corresponding transponder on it. It hears that ping and then it replies back with a chirp. And so if you know that round clock time and you know the velocity of sound through water, you know what that range is. And the USBL goes even further, and by having multiple piezo elements packed into the head, you can do beam forming or phase delay estimation to actually get an azimuth and elevation estimate of where that signal came from. So then you've got range.
So you end up with a ball of piezos. It's not all in one plane. In order to get elevation, you're going to need at least 2 planes.
Yeah.
And anybody who listened to the ShotSpotter episode, yeah, it's the same thing. But acoustics through water, temperature, the speed of sound through water depends on temperature.
Yeah, and
fish.
More broadly, density. So the density of the water is a function.
Salts.
Is a function of temperature and salt. And turns out when you go really deep, water is actually not quite incompressible. That assumption begins to break down.
Boy, is that a weird environment.
Yeah. And so when you're really making a deep dive into navigation, you'll actually look at these sound velocity profiles in the water. And this is a plot of sound velocity as a function of depth. And it's this kind of, depending on what the characteristics are of the water, it can be this kind of convoluted shape. And as a result, you end up with the sound waves taking not a direct line through the water. They'll actually bend and refract and change. So they don't travel in a straight line as you're moving through these layers of water. You could almost think of it as a finite model. Each 5 centimeter section of water has a slightly different velocity.
Like a yogurt parfait.
Yeah. And just like, we rely on that in optics. It's the same principle. The light travels at a different velocity through different materials, and then we shape those materials, and that defines where we bend effectively the light. So the same thing's happening underwater with sound.
And the same things happen with GPS.
Yep.
That if you're in a city, it's much worse because it gets the reflections from the buildings, and it's like echoey, except in GPS ranges. Mm-hmm. And so how do you fix that? I mean, it's more than just knowing it's there. It's how do you compensate? Do you compensate, or do you just accept the error?
I think it depends. If most of my work has been fairly mission driven, and so it's what is an acceptable error for the scientists using this system? If it's X, okay, well then that first order approximation, let's just call it 1,500 meters per second, and we'll call it good. And anything else, we just don't worry about. But you can get really complex, and you can do things like there's something called a bellhop analysis, where you actually simulate a water.
Do you tip it afterwards?
No, but you do a numerical ray tracing analysis of sound through water, and then you can put that into your navigation model. I haven't gone to that. I haven't had to do that degree of engineering and modeling for these navigation systems, but I've talked to and worked with people who have, and they've kind of said, it'll buy you a little bit, but oftentimes it's just not worth it, and that first order approximation is good enough.
And wouldn't it be simpler to just have another station doing the pinging?
Yes. Yeah.
Because, and once you get 4, you get good location.
Yeah. And so I just talked about ultra short baseline, where you're getting that range and azimuth elevation from a single unit. But if you have multiple acoustic instruments, perhaps that are spread out over order kilometers on the seafloor, you typically would refer to that as a long baseline system. And then you're measuring ranges against things that have a known fixed location. And then you can use, more traditional TDOA, time difference of arrival methods, or even, just finding the minimum, or, linearize the system and then do a least squares on your position. And then that tends to be pretty good.
What was the neatest animal you saw under the ice? I mean, did you see any of these giant sea stars or jellyfish or weird things that shouldn't exist on this planet?
Yeah. So one of my colleagues down there, who was a graduate student at Moss Landing, he was an under ice diver. So he was going down and collecting samples and would put on dry suits. And he showed me a video that he took of a giant jellyfish that was hanging out near the outfall, which is where the treated water leaves the station. And I couldn't quite get the scale of this jellyfish until he, started the camera looking at the outfall, and he was like, the diameter of that pipe, I don't remember exactly. It was like 12 or 18 inches, right? And then he starts panning up, and there's just like multiple pipe diameters, like mini pipe diameters, until he gets to the bell of the jellyfish, and the tentacles were hanging on. So the tentacles to this jellyfish were like 30 feet long. And he said the bell of that jellyfish was like 6 feet wide. I was just dumbfounded, like a jellyfish bell that's 6 feet wide. I can't even imagine swimming next to, encountering something like that in the water.
Yeah. Were you ever tempted to do an under ice dive?
I'm not a scientific diver, so I couldn't just, throw on a wetsuit and go and do it. But it certainly seems beautiful. I mean, the pictures that we would, most of the time we were operating the ROV down there in open water, and we couldn't see the bottom, but closer to some of the edges when we could actually get down and see the benthos. Holy cow, it was phenomenal. I mean, I never would have thought that there are so many critters living on the bottom of the ocean in Antarctica. But there are sea stars and pycnopodia, which are these kind of spider-looking things crawling all over one another, and massive sponges. And I mean, it looks like a rainforest, but with, underwater critters. It's phenomenal.
Where do the nutrients come from? Is it all from the phytoplankton?
I'm not the right person to know that. No, but that's a good question. I mean, I should know.
Would you like me to ask you about ROVs?
No. That was just my way of saying I don't know. And I'm a little, ashamed that I don't know. But so, generally nutrient cycling in the ocean, you get upwelling, where you get a lot of nutrients that are brought up from the depths. I'm not sure if those nutrients fundamentally come from the depths. I mean, I know there's lots of cycling. I know a lot of the iron in the ocean actually comes from deserts and wind that picks up little pieces of sand and then deposits iron out across the ocean. So the Sahara Desert actually does a tremendous amount for fertilizing the Pacific Ocean, because that dust blows over and then lands out there, and that's, oftentimes a limiting nutrient for things like algae.
Yeah, there's this interesting idea that you can dump iron filings into oceans in order to sequester carbon. Boy, am I off topic. Okay, let's see. I have a question from Bailey, and I know the answer to this one, and it is awesome. Have any animals attacked anyone's ROVs? And what happens? Yeah.
So there's a video on YouTube from an early Trident user, and I think they're operating down in the Farallon Islands with great white sharks. And the video starts out with the Trident sitting out in the water, and you see a great white shark come up and swim and do what I was told was, an aggressive, get out of here kind of behavior. And then she comes back and then makes another pass. And on the second pass, bam, just, chomps down on the ROV. And you have this first person view. And so all of a sudden you're literally like looking in the mouth of this great white shark at these teeth. And so she kind of chews it for a minute and then spits it out, because clearly it doesn't taste like anything. And so the shell is all scarred, but it survived, and they continued diving with the vehicle for the rest of the day. So,
yeah, and
then you bought it back and used it for advertising.
Exactly.
This video is amazing. I mean, it starts out third person. You see what happens, and you're like, "Oh, well, they lost their thing." Yep. But no, you look inside of a shark's mouth. Yeah. It was kind of scary. Mm-hmm. Mm-hmm. Have you had other things like that? Interesting animal encounters or actually lost units due to wildlife?
No, I haven't. We almost got a unit, our skinny ROV stuck out in the ice when we were operating a little too close to the ice edge, and the wind had rafted and blown a whole bunch of broken up ice back to close to where we were working. And I took it out into the open water, and then the tether got tangled up in this rafted ice that kind of looks like, rubble from a building after an earthquake or something. And so it was like 4 very tense hours of just trying to untangle this, tether. And we're thinking like, at about hour 3, we're like, well, are we going to have to go get somebody who knows how to dive and who can like go and untangle this, so it was just,
we're going to need a bigger hole.
Yeah. Well, that's what we started doing. We're like, we didn't know quite where it was because we were out along horizontal range and the USBL wasn't quit working. So, it was tense, but we recovered the vehicle and the tether.
Let's see. If you could deploy ROVs anywhere, where would you take them and what would you want to look at?
I think there's so many cool ecosystems out there. In our own backyard here in the Monterey Bay, we have these phenomenal kelp forests, which are actually extremely difficult to operate.
Yeah, I was about to say, the tether might cause some issues there.
Yeah, they get tangled. But the life there is just phenomenal. Coral reefs are obvious ones. And what I think would be so cool to be able to do with this is if you can live stream these experiences over the internet. And I'm envisioning a classroom that gets shipped like a big Pelican box that has a bunch of VR headsets, and the kids can all put these headsets on, and the vehicle has a 360 view camera. And so it's like Miss Frizzle's Magic School Bus,
Yes.
and you're getting a tour of this kelp forest or the coral reef, down in Australia. So that's kind of more of an experiential thing. But yeah, I would also like to kind of embark on the challenge of like, how cheaply could we make an ROV or an AUV that would go to the bottom of the Marianas Trench? I mean, folks from Woods Hole, James Cameron have been down to the bottom of the Marianas Trench, but could you do it with $10,000 of hardware? I mean, engineering time aside, like what would it actually, how could you get down there and how cheap could you do it?
I mean, the pressure is way more. So you have to deal with the pressure, but what are the other factors?
Maybe you don't have to deal with the pressure. So you can oil fill electronics and you can have everything be pressure compensated.
You don't have to put a human in it. So
Yeah.
But then you have to get in, you need to find, you need to be careful with your chip selection, because things like crystals have little air cavities in them, or MEMS devices have air cavities that, are open because the little elements in there need to vibrate. Even some memory devices have little air pockets in them. So if all of a sudden
that's not usually on the data sheet either.
Yeah, no. I think, people have businesses about doing, pressure compensated electronics for very specialized needs. So the electronics is one thing, but I think you can get around that with just selecting the right stuff, and then you fill everything with oil and let it go to 11 kilometers of pressure. So tethers, if you wanted to have a tethered vehicle, that's actually also pretty difficult.
Because that gets really heavy.
Gets really heavy, and after depending on what the tether is made out of, a lot of oceanographic vessels have a standardized, I think it's a 0.68 inch steel braided tether that's got some copper and fiber on the inside of it. But I think those, I haven't done the math, but they become non-self-supporting after like 8,000 meters or something. There's just too much weight and they snap. And so then you could, the way some folks at Woods Hole got around this was they had simultaneous unarmored fiber spools both on the vehicle and on a little depressor that lived just below the water surface. So as the vehicle is descending, you're simultaneously spooling out an unarmored fiber optic cable, one end from the vehicle and one end from the ship, and you just let the current take that cable wherever. So you've got, easy gigabit comms down to the vehicle. It's not a structural thing. And then you build in, backup redundant acoustic systems and failure safe mechanisms and all those sorts of things. But then all of a sudden, you basically have a weightless cable that gives you comms. So, okay, if we can do that on the cheap, or maybe there's another way to do it. Maybe you do just make it autonomous. Cameras, the airspace dealing with air and pressure does get kind of interesting when you're thinking about cameras again. Because if you're going to go to the bottom of the ocean, I would think you want to see what's down there.
We're going to need a camera, maybe 12.
Yeah. Maybe that little door is down at the bottom. So we got to find that.
Remember, don't take out the plug.
Yeah. But I think you can also play kind of an interesting materials game there. Most of the time we use glass in our optics, which has a certain, I'm not as well versed in this, but Snell's law is, I think, what determines how the angle of light changes, and that's the function of, I think, just the density of the material. I don't actually remember what all
there's
goes into
some electro-optic stuff too, the chemical stuff that affects it, but index of refraction.
Blah, 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 material science.
Yeah. But I've been told by some people who have thought about this, that if you make your lenses out of like sapphire, for example, then the index of refraction between water and sapphire is roughly equivalent to that of air and glass. So all of a sudden, now you don't need to maintain an airspace, in your camera or your lens or anything like that. So then you're kind of in business. You don't need a pressure housing, which is an expensive part, and you still kind of have to figure out the tether comms part. But yeah.
Okay, this is from Stephen, and it's related to what we're talking about now. What are some of the key fundamental technology challenges that are currently limiting progress of ROV development? And he suggests comms bandwidth, navigation, positioning, mechanical.
Yeah.
What do you think is the most important?
Well, one of the things we haven't talked about is connectors. Underwater connectors are the bane of many underwater engineers' existence, or at least I spent way too much time dealing with connectors.
I've worked with military connectors, and I suspect that that's a level of harder that's exponentially harder than the freaking military ones, which are so much harder than regular.
Yeah. And they're expensive. I mean, even the lowest end connectors, you're like looking at $100 a pop, and you're
like, Raspberry Pi
$35
connector.
Yeah.
It's just
$100 for the cheapest one.
Yeah.
Yeah. So if we can figure out a good way to make, those connectors that can transmit a lot of power, and you end up having to trade off voltage and current, based on conductor size.
Especially when you're going 8,000 meters.
So yeah, connectors are a big one. The navigation is also a big one. These navigation systems, if you have hundreds of thousands of dollars to spend, like, you can build a pretty phenomenal navigation system. You can get laser ring gyros or fiber optic gyros, which are actually measuring the rotation of the Earth.
Yes. And
combined with knowing where the gravity vector is, you can get an estimate of true north. So that's how those compasses work. But those are like $150,000, compasses.
Well, I mean, you can get $5,000 ones, but they're not that much better than MEMS.
Yes,
but maybe
correct.
they don't have air.
Oh boy, MEMS gyros and everything. Like, I don't think you're not going to have a true north gyro compass out of a MEMS device. I think that the noise floor is just too high. So yeah, navigation, also tough one. We kind of like figured out the motor things. Like, you can actually put brushless motors as long as you've got good enamel coating.
And as long as you wash them off after you get them out of the salt water.
Yes, they will certainly last longer if you do that. We've done a fair amount of testing with not rinsing the motors, because we do these kind of rapid life cycle testing on the motors, and
it's not called being lazy at all.
And they'll still do quite well. The abrasive properties, if you set the ROV down in a really silty environment, and especially a silty environment that has lots of ferrous material, because these are permanent magnet brushless motors, all of a sudden you start accumulating the black fuzz. If you've ever dragged a magnet through play sand, that starts accumulating in the motor, and then that abrasion is usually what kills you before the salt water does.
Let's see what other questions did I get from listeners. Svek wanted to know, before going to Antarctica, what did you expect to miss the most? And once you were there, what did you actually miss the most?
That's good.
It wasn't sunlight, because it was summer.
I was expecting to mostly miss coming from California, like lots of fresh vegetables all the time. And at the beginning of the season, when there's lots of big cargo planes coming in, we actually have a pretty good supply of what we call freshies. And those tend to taper off. But, then it's okay. The thing I ended up missing the most, though, was sleep. I'm definitely like an 8 to 9 hours a night kind of guy. And when you're down doing field work, that just doesn't happen. And so, I kind of get progressively more and more underslept as the season goes on. So that's a hard one for me.
But you went back for 3 seasons.
Yeah.
That seems like a lot. What made you stop going back?
The NSF grant ended, and then it was like, what should I do now? How about grad school?
What were you doing with the other months of the year while you were doing that?
So I did a little bit of contract work for OpenROV. I worked as an intern at the Monterey Bay Aquarium Research Institute at one point. We had work to do in the off season, making repairs and improvements to the vehicles themselves. And then a few other small contract things on underwater, platforms.
What does it take to keep the robots working in Antarctica? Is it different than the problems you're seeing with the Trident, just making it work underwater?
Yeah, so the vehicles we had, the skinny vehicles that we had down in Antarctica, were a pretty complete prototype vehicle. For it to be what I would consider a production vehicle, we would have needed another spin on it. And mostly we ended up dealing with, so there was not, a good example was we didn't have very good strain relief on a handful of these underwater connectors. There was just a little bit of residual strain in there.
$1,000 connectors, and they couldn't build in some strain relief.
Yeah. And so, every, probably on average, like 3 or 4 weeks, one of these connectors would fail. Just a little bit of water would start getting in, and the power bus on Skinny was a 300 volt DC power bus. And a little bit of salt water can go a long ways with 300 volts. And so all of a sudden you would end up, there would be arcing underwater. And usually the symptom would just be that the vehicle would go dark because it would short everything out. And, at one point we actually cooked it shorted out. And then some of that 300 volts made its way onto the RS-485 comms bus and destroyed the RS-485 transceiver that I had in there. And spent hours trying to figure out what was going on. Couldn't find it. And then I had a dentist smear, and I'm, digging around, looking in the inside of these circuit boards that are all kind of sandwiched together, and see what looked like a lightning crack, through the middle of the 8-pin dip. And I was like, oh, I don't think that's supposed to be like that. And so that became a quest for like digging around for, I don't remember what chip it was specifically, but I don't, find a spare for that. Okay. And solder it back in, and hey, we're back in business,
So you had to do the hardware and soldering.
Uh-huh.
How do you solder in a tent in Antarctica?
With a lot of patience and, some thick skin, like especially if there's a storm outside and it's blowing. But we had, so in our field camp out on the ice, we had a small solar array with lead acid batteries. And if we really needed to, we had some small gas powered generators if it had been cloudy for a couple of days and the batteries weren't up to snuff. But Skinny itself was powered by a small portable Honda 1 kilowatt generator that we would then put through a standard APC computer battery backup to clean the power up a little bit. And then we would up convert to 240 volts, pass that down the tether so that we're not pushing a whole bunch of current over a 300 meter tether. So boost the voltage up, send it down, and then take it down to lower voltages on the vehicle, which is actually very common in ROVs. A lot of the professional ship-deployed ROVs have like 4,000 volt DC systems going down the tether.
I mean, that totally makes sense, because then you have the high voltage, you can have the super low current. But then when you talk about things like salt water, it does seem like the compatibility, the trade-off there is, I don't know. I'm not sure about that. Are you sure?
I mean, a lot of people who are smarter than me, I think, have also converged on this solution, so I'll go with it.
Okay, I wanted to ask you about methane seeps because you mentioned that was a hobby, and I have some strange hobbies, but methane seeps was never one of them. What do you mean by that?
Yeah. So methane is a really potent greenhouse gas. It decomposes naturally in the atmosphere. It has a half-life between like 8 and 12 years. And so methane, which is CH4, decomposes into carbon dioxide and water. But before it does that, it traps a lot more heat than carbon dioxide. So depending on the time scale that you're talking about, a lot of folks have kind of standardized over a 100-year equivalent, but a ton of methane is roughly equivalent to 25 tons of CO2 over a 100-year time period. So it's a potent greenhouse gas. And people have been thinking and talking about this in relation to cows and their methane emissions.
That's where I've heard it.
Rice paddies, as well as coal mines, old oil and gas infrastructure. So those are kind of the primary sources. And a good friend of mine who works in the climate space started thinking, well, what are we going to do about the Arctic? People are talking about these positive feedback loops that occur when you have, for example, melting permafrost, and then more CO2 and methane gets emitted through the ground as a result, and then that induces more warming and more melting of the permafrost. And it turns out that there are some relatively large point source releases of methane throughout the world, and large as in like there's a lake where we're collaborating with some folks from University of Alaska Fairbanks, and it's in some parts of this lake kind of like a jacuzzi where there's bubbles bubbling out from the bottom of the lake, except it's all natural gas, and it's a lot of methane. So then the question is, well, can we do it? Like solving the problem of plugging up cow farts is pretty hard because there's many cows, and they make on average a little bit per cow. So that's a very hard thing. But if you have large single point sources, that's a more tractable problem. If your goal is to reduce overall emissions. So I'm working with a group of folks, and we're working on a device to mitigate those emissions. And
I remember driving through Montana many years ago. They had basically lit some of the methane seeps on fire.
Yeah.
To partially offset.
Mm-hmm.
Was it offsetting, or they were just burning off the fields?
I thought it was partially to offset the emissions of the greenhouse gases.
Yeah, so that's actually that's done at landfills.
Okay.
When they cap them, with the decomposition of the organic material, you will generate methane. And some landfills will burn that methane, and it's as I mentioned earlier, it degrades into CO2 in the atmosphere.
Which is better than methane.
Yeah. So if you can just accelerate that transition from methane that's already going to get released into the atmosphere, it's better if you can just shorten that transition time. And then and
there's a better chance that the CO2 will fall immediately out.
Yes. Yeah. I mean, when you combust it, in theory, if you have perfect combustion, you end up with carbon dioxide and water.
I was thinking of the stuff they do in natural gas fields where there's burning off the excess which is not for environmental reasons at all. It's just because they don't know what to do with it.
Yeah. Yeah. I mean, they're drilling like an oil well, for example, but there's a little bit of gas in there and they need to do something with it, and they don't want to just release it.
And you don't want it to build up.
Correct. Yeah. Yeah.
Okay. I should go back to the ROV, the open ROV, because that's technically why you came. You guys are selling these, but they're kind of expensive.
Yeah.
How much are they?
I think they're retailed for $1,700 on openrov.com. I was able to get a discount coupon code, so if anybody is interested, if you use the code word embedded, and I think we'll drop a link in it in the show notes. Yeah. But that'll get you off $200 in the store, so that should show up at checkout time. But on the grand, like, you didn't used to be able to get an ROV for $1,700. It used to be that the lowest class was like $100,000, and then people started making them for $30,000, and now it's like same order as a DJI drone kind of thing.
Yeah, that's a good comparison. And do people do people send you videos? Are there places where I can look and see what people are doing with them?
Yeah. So there's an awesome initiative that we have going on in collaboration with National Geographic and the Packard Foundation, the Schmidt Ocean Institute, called the S.E.E. Initiative. And these are, we got a grant that allows us to give ROVs out to citizen scientists, explorers, people who are just doing really interesting, engaging work. And so if you do a search for S.E.E. Initiative, you can see all these expeditions that people are going on with the ROVs. There's folks working on turtle monitoring. There's folks here in the Monterey Bay. Some people working in the Monterey Bay marine protected areas and using these ROVs as monitoring tools. And it's a lot of really awesome stories. Yeah.
And I'll point out, since I searched for the wrong one, it's S.E.E.
Correct.
Not S.E.A. So
Correct.
C as in Visual Sea Initiative.
Yeah.
As though you were looking through a camera at some amazing animal.
Yeah. Science Engineering Exploration Initiative, I think.
I'll have a link to that.
Yeah.
Science Exploration Education.
Yes. Thank you.
It helps to have the website in front of me.
Yeah.
My Googling skills are second to just about everybody's. What else should I ask you about? I mean, you have a pretty broad resume, and I'm like, let's go back to navigation. Let's talk about acoustic sensors. Let's talk about acoustic modems. Let's talk about Antarctica. Just, what do you want to talk about?
I don't know. I mean, I feel like it's always fun to talk about like dream projects or the things that you would want to work on if you were given a chunk of free time and money for prototyping and that sort of stuff. I've always been interested in trying to do low cost acoustics. It's a space that I know very little about. And so, I'm sure there's all sorts of gotchas in there about, what makes it really hard. But I look at, how cheap, consumer audio equipment is. And it's like, okay, so we have, pretty good, A to Ds and D to As that, are good to like 440, kilohertz. So you can do anything in the acoustics range, from 20 kilohertz and below. Okay. What could be done using consumer grade stuff, instead of having to go really, really high up.
Is this for exploration, for location?
Yeah, I guess both for location. Some of the other navigation instruments, that I didn't talk about are, one of them is called a Doppler velocity log. And this is an instrument that uses acoustic Doppler shift to measure three-dimensional velocity. So it sends out pings, and you can imagine, when the ambulance is driving towards you, the pitch of its siren is higher than when it goes past you, and that's due to Doppler shift. And we can use that same principle underwater to measure velocity of a vehicle relative to the ground, or you can also use the same thing to measure water velocity, but the sound, in essence, reflects off of little things in the water or the sea bottom. And so if you have a good velocity measurement, that goes a long way in helping you out with your navigation system, because then you're not just relying on acceleration.
Acceleration's a terrible measurement.
Yeah.
Because we have 1 G of acceleration on us at all times, and therefore anything else is tiny compared to that.
Yeah, yeah. So having that acoustic velocity measurement would be awesome, and also, it goes a long way if you're going to do an autonomous or untethered vehicle, having that acoustic back channel to the vehicle, so that you can actually command it to come home or, send a little bit of data back periodically. This
is the acoustic modem style thing. Have you used acoustic modems much?
A little bit, yeah. I've used some, a modem from Trident. They're a company based in the UK. And then I think that's actually the only one I've touched technically. But
I'm looking at one that is 600 baud, and I'm just like,
yeah.
I don't, that's like, I can speak 600 baud.
Yeah.
I feel like I could chirp to it like R2-D2. It's just so weirdly slow. I have my serial port turned up to 1 megabit per second.
Yeah.
How do you live this way?
You get very diligent about byte packing. What is the data that you actually want to send to the vehicle, and what is it that you need back, and what can you what if so there's in the underwater world, you have not only the problem of very low baud rate, but you have high latency, right? If your vehicle is 1.5 kilometers away, that message is going to take a second to get to you. So you can't do really timing critical stuff over that much latency. Oh, and by the way, those sound waves don't travel in a direct line, and they might bounce off of the underside of the ice, and you might not actually ever get that packet.
I have noticed it does seem to be like talking into a tin can through a wet noodle to the other side.
That's a good analogy. I like that.
It's not exactly a precision instrument there.
Yeah. But I mean, my sense is that there is a tremendous amount of digital signal processing that has gone into these systems, and you do have error correction when they packetize this data, so you do have some assurances there, and you can check your checksum and do that kind of stuff. Okay,
what else would be on your just give me a genius grant, I'll do what I want to do.
I think another kind of selfish program is I would like to I've always thought it would be kind of interesting to roll a GPS from scratch. From that sounds a little perverse.
I was at a company that did that.
Really?
Just wrong.
But they wanted to ship. Don't you need some rockets first?
I think he just wants to do the ephemeris calculation and all of that.
Oh, okay.
Yeah.
Okay. I suggest doing it in Postgres or SQL, because that will make a really good conference talk.
Okay.
That was not a helpful suggestion.
But that it just seemed like I tend to think about, I'm also one of these people who starts a lot of projects and doesn't finish most of them, but most of them are it's a learning exploration. It's a way for me to dive deep on something kind of particular that I'm interested in. And then once I've extracted that nugget, then I'm like, okay, I'm ready to move on. I've, learned what I want to there.
Oh, and I could see GPS. That makes sense, because it is so critical to navigation, and they have made so many amazing things possible. What's hidden in that code that you just don't think about without doing it yourself?
Yeah.
For all that, I don't think that's a good idea. For me, for you, it may be awesome.
Yeah. No, I mean, it sounds hard, and maybe it is just maybe if I just did the math part of it, I would feel fulfilled.
And maybe somebody will let you read their GPS code.
Yeah.
All right. I think we have kept you long enough, since this is one of the first sunny weekends in a long, long time. And it's almost not cold for Christopher.
I don't know. Let me look. No, I don't have that up. It's probably on the border.
Yeah. It may be 61 F.
Yeah.
He's still got a sweatshirt on. All right. Do you have any advice for people who want to follow a career path like yours?
I would say, especially if you're doing field robotics and field work, patience is a really key thing to develop. When something breaks, and it will, even in the most stressful environment, it's pretty key to keep a level head and be able to put your head down and keep moving forward. But also, I guess know when to walk away, take a little break, and come back, and then get back to attacking it. So that, and just be really curious, don't hesitate to take a little bit of time and go on those, kind of deep dives, something that you're interested in, because you never know when that's going to come back and be useful. Oftentimes it is.
All right. I think I may have preempted my last question, but before we get there, I will remind people the code embedded for $200 off at the Trident store. If you are getting your own ROV, please let me know and send me all your videos.
Or let us borrow it, and we can go check out the inside of the boat and see if there's really a giant octopus living in there.
Yeah, did you bring one? Because I really want to go down to that concrete ship and see what's living inside.
I'll bring one once the dust has settled a little bit at the office. Yeah.
All right, Laughlin, are there any final thoughts you'd like to leave us with?
Oh, no, thank you too just so much for having me on. This has been really fun.
Our guest has been Laughlin Barker, systems engineer at OpenROV. You can find them at openrov.com. Thank you so much for being with us.
Thank you.
Thanks, Laughlin.
Thank you also to Kathleen Toot of Pie Santa Cruz for introducing me to Laughlin. Thank you also to Christopher for producing and co-hosting. And of course, thank you for listening. You can always contact us at show@embedded.fm or hit the contact link on embedded.fm. And now a quote to leave you with. Yes, from Helen Scales. She wrote Eye of the Shoal, which I believe Christopher named the Fish Facts book. Before 1815, when Humphrey Davy invented his safety lamp, British coal miners sometimes went to work carrying a bucket of dead fish. Naked flames had the dangerous tendency of blowing up any methane that seeped into the tunnels, so miners needed alternative lighting sources. A bucket full of putrefying fish could apparently produce enough dim, cold light for miners to see by. I hope you enjoyed that fact. I'm not sure I did. Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.